The first thing we have to do is discuss the focus of 6001. What's this course really all about? That seems kind of obvious. This clearly is a course about computer science. But in fact, we're going to claim in a rather strange way that that's not really true. First of all, it's not really about science. It's much more about engineering or maybe even art than it is really science. Secondly, it's not really about computers. Now that definitely sounds strange. But let me tell you why I say it's not about computers. It's not about computers in the same way that physics is not really about particle accelerators, or biology is not really about microscopes, or geometry is not really about surveying instruments. In fact, geometry is a good analogy to use here. Geometry is an ancient term, comes from two words, gia and metra, which means earth and measure. And to the ancient Egyptians, that's exactly what geometry was about. It dealt with measuring the earth or doing surveying. And the reasoning was very simple. After the annual flood of the Nile, they need to reestablish the boundaries of the land that belonged to different people, and they had to go back and do the measuring to make sure they knew where those boundaries were. In retrospect, of course, we know geometry is much more than just dealing with surveying instruments. What the Egyptians were really doing was formalizing a particular kind of knowledge that dealt with things that were true. They were creating axioms for how to deal with reasoning about geometric entities. This analogy is true for a lot of fields. When a field is in its infancy, it's often easy to confuse the field with its tools, or if you like, what the core of the field is about with the tools that are used to measure it. In retrospect, we saw Egyptians were really dealing with axiomatic knowledge, even though at the time they thought they were just dealing with surveying instruments. So in fact, geometry is really dealing with a particular kind of knowledge, known as declarative, or what is knowledge. By analogy to geometry, computer science isn't really about computers, it isn't really about the tool, it's about the kind of knowledge that computer science makes available to us. And what we're going to see in this course is that computer science is dealing with a different kind of knowledge. It's dealing with imperative or how-to knowledge. It's trying to capture the notion of a process that causes information to evolve from one form to another, and we want to see how we can use methods to capture that knowledge. Let's stress this a little bit better. What's declarative knowledge? It's knowledge that talks about what is true. It makes statements of fact that one can use to try and reason about things. For example, here's a statement of truth about square roots. The square root of x is that thing y, such that y squared equals x, and for safety y is also greater than or equal to 0. Notice that this is a statement of truth. It says if somebody hands you a possible value for the square root of x, you can check it to see if it's correct. But it doesn't tell you anything about how to find the square root. On the other hand, imperative knowledge deals with how-to kinds of information. It tends to describe specific sequences of steps that characterize the evolution of a process by which one can deduce information from one set of facts to another. So here, for example, is a very old algorithm for computing the square root of x. And it says, very simply, let's start with an initial guess, call it g. Let's improve that guess by taking g and x divided by g and averaging them. And let's keep doing that until the guess gets good enough. Okay, let's test it out. For example, if we want to compute the square root of x where x is equal to 2, we can see how this set of steps describes a how-to way of getting that information. So here we go. We've got a little chart. We have x equal to 2. We have g equal to 1. Our algorithm says let's improve the guess by averaging g with x over g. So that gives us x over g equal 2, and now we can improve that guess by taking g and x over g, averaging those, which gives us a slightly better guess for g. We can check and see we're not really close enough, so we keep doing the same process. We take x over the current value of g, we take the current value of g, we average those, and we get a slightly better guess. And we keep doing that until we get a guess that's good enough. So notice how this little algorithm, this little method, describes a sequence of steps. It tells us how to do something, how to find the square root. Whereas the previous case, the imperative case, or rather the declarative case, simply told us how to recognize the square root. So what we've seen is that imperative and declarative knowledge are very different. One captures statements of fact. The other captures methods for deducing information. It is easy to see why the latter is more interesting. For example, one could in principle imagine trying to collect a giant listing of all possible square roots, and then simply looking up a square root when you need it. Much more convenient is to capture the process of deducing a specific square root as needed. Thus, we are primarily interested in how-to knowledge. We want to be able to give the computer instructions to compute a value, and this means we need a way of capturing the how-to knowledge. In particular, we want to describe a series of specific mechanical steps to be followed in order to deduce a specific or particular value associated with some problem, using a predefined set of operations. This recipe for describing how-to knowledge we call a procedure. When we want to get the computer to actually compute a value, that is, use the how-to knowledge to find the value associated with a particular instantiation of the problem, we will evaluate an expression that applies that procedure to some values. The actual sequence of steps within the computer that caused the how-to knowledge to evolve is called a process. Much of our focus during the term will be in understanding how to control different kinds of processes by describing them with procedures. Now, we want to create tools that make it easy for us to capture procedures and describe processes. And for that, we're going to need a language. Whatever language we choose to use to describe computational processes, it must have several components. First, it will have a vocabulary, a set of words on which we build our description. These will be the basic elements of computation, the fundamental representations of information, and the fundamental procedures that we will use to describe all other procedures. Second, it will have a set of rules for legally connecting elements together. That is, how to build more complex parts of a procedure out of more basic ones. This will be very similar to the syntax of a natural language, like English. Third, it will have a set of rules for deducing the meaning associated with elements of the description. This will be very similar to the semantics of a natural language, like English. And finally, we'll need standard ways of combining expressions in our language together into a sequence of steps that actually describe the process of computation. We're going to see that our language for describing procedures will have many of the same features of natural languages, and that we will build methods for constructing more complex procedures out of simpler procedures in natural ways. One of the things we'll see is that it doesn't take long to actually come up with the rules for connecting things together in our language, nor for coming up with the rules to deduce meanings associated with those things. Our real goal, of course, is to use this language of procedures to solve problems of interest to us. And indeed, much of the term will be spent on taking that language of procedures and seeing how one can use it to actually control complexity in very large systems. In order to capture imperative knowledge, we are going to create languages that describe such processes. This means we will need to specify a set of primitive elements, simple data, and simple procedures, out of which we will capture more complex things. We will also need a set of rules for combining primitive things into more complex structures. And once we have those complex structures, we will want to be able to abstract them, to give them names so that we can simply treat them as if they... We will see as we go through the term that this cycle of creating complex processes, then suppressing the details by abstracting them into black box units, is a powerful tool for designing, maintaining, and extending computational systems. Indeed, that is precisely the goal of understanding computation. How can we create methodologies that make it easy to describe complex processes without getting lost in the details? Clearly, a well-designed methodology for thinking about computation should enable us to build systems that robustly and efficiently compute results without error, but also should enable us to easily add new capabilities to the system. Thus, our goal is to gain experience in thinking about computation, independent of language details and specifics, in order to control complexity in large, intricate systems. Our real goal in 6001 then is to use the idea of a process and our way of describing that process with procedures in order to deal with complex systems. We don't want to just build small programs. We want to build programs that do something interesting. And almost by definition, doing something interesting is going to require us to deal with the complexity of some problem, and we need tools for handling that complexity. We're going to see several key concepts in terms of dealing with abstract engineering or controlling complexity. The first is what we might call black box abstraction. Suppose I have that concept of the square root, and in fact I've shown you details of one way to find them. But in general I just want to use square roots to do something. In this case I should be able to take the notion of the square root, which is why we give it a name in fact, and take it without having to worry about the details and just use it. We can think of building a black box in which captures this abstraction so that we isolate the details from the actual use. We're going to use that tool of abstraction, that black box sort of notion, both for procedures and data as a key way to try and control complexity. Not only are building black box abstractions a valuable tool for isolating out the components of a system, but they also provide us a mechanism for reasoning about how they connect together. And indeed, in most systems, a key issue will be how do we take those pieces, how do we take those modules, and stick them together in ways that allow us to do something more complicated. This means that we're going to need conventional interfaces for putting modules together. This is much like, by analogy, dealing with a stereo system, in which we can buy components from different manufacturers and have standard ways of interfacing them together to get out the systems that we want. In programming, we're going to have the same idea, and we'll spend a fair amount of time talking about conventional interfaces for gluing together abstractions. And in fact, here are three of the kinds of things we're going to deal with throughout the term as examples of conventional interfaces. We'll see as we go through the term that building black box abstractions and finding ways to conventionally interface them or glue them together is going to be very valuable. But even with these kinds of tools, there are still some problems that are too complex to handle in a convenient way. When we reach that stage, we're going to generalize one more level and build our own language. We're going to use the notion of metalinguistic abstraction to create separate languages specifically designed for problem areas. We'll find that this is a powerful tool and will require us to look at the notion of what it means to evaluate expressions in a language. And as a consequence, we'll see several examples of different ways of building languages. Languages for new problems, languages that deal specifically with interfaces to hardware, evaluators of various forms, and finally dealing with compilation as a specific way of manipulating those programs. Our goal in this course is to explore computation, especially how thinking about computation can serve as a tool for understanding and controlling complexity in large systems. Of particular interest are systems in which information is inferred from some set of initial data, whether that is finding other information on the web, or computing an answer to a scientific problem, or deciding what control signals to use to guide a mechanical system. For such systems to work, they need some process by which such inference takes place, and our goal is to be able to reason about that process. In using computation as a metaphor to understand complex problem solving, we really want to do two things. We want to capture descriptions of computational processes, and we want to use the notion of a computational process as an abstraction on which we can build solutions to other problems. We will see that to describe processes, we need a language appropriate for capturing the essential elements of those things. This means we will need fundamental primitives, or atomic elements of the language, means of combination, or ways of constructing more complex things from simpler ones, and means of abstraction, ways of treating complex things as primitives so that we can continue this process. So let's begin our discussion of a language for describing computational processes. To do this, we really need to provide a definition of, or at least some intuition behind, the idea of a process. In simple terms, a computational process is a precise sequence of steps by which information, in the form of numbers, symbols, or other simple data elements, is used to infer new information. This could be a numerical computation, such as a set of steps to compute the square root, as we saw earlier. Or it could be a symbolic computation, finding a piece of information on the web, or some other inference based on information. While the computational process refers to the actual evolution of information in the computation, we also want to be able to capture a description of the steps in that computation. We refer to this recipe as a computational procedure, a description of the steps of the computation. Thus, our language will allow us to describe recipes and to use these descriptions on particular instances of problems. That is, it will allow us to bake solutions using those recipes. First, we need to understand how we're going to represent information, which we will use as a basis for our computational processes. To do this, we need to decide on representations for numeric values and symbolic ones. Let's start with numbers. To represent a number, we begin with the most atomic element. Because ultimately we will represent information inside the computer, we will use electronic signals to do this. These are most conveniently represented by using a high voltage or current or a low voltage or current to represent fundamental values. And thus the most primitive element in representing a value is a binary variable, which takes on either a value of 0 or a value of 1. This variable represents one bit or binary digit of information. Of course, we need to group these bits together to represent other numbers, which we do typically in groupings of 8 bits, called a byte, or in groupings of 16, 32, or 48 bits, often called a word. Once we have sequences of bits, we can use them not only to represent other numbers, but we can envision encodings in which numbers or bit sequences are used to represent characters. And characters can further be grouped together to represent symbolic words. Though we won't worry about it much in this course, there are standard encoding schemes for using bit sequences to represent characters as well as numbers. Typically, the first few bits in a sequence are used as a tag to distinguish a number from an encoding for a character. Now, let's spend just a second thinking about binary representations for numbers and operations to manipulate them. We said we could use a sequence of bits to represent a number, for example, a positive integer. We can identify each place in the sequence. By convention, the lowest order bit is at the right. And we can weight each bit by a different power of 2, so that we're able to represent all possible integers, up to some limit based on the number of bits we're using. Mathematically, we can capture this in the equation shown on the slide, and this gives us a way of representing unsigned integers. Now, what about simple arithmetic operations on binary integers? Well, the rules for addition are just what you'd expect. And we can do standard addition by simply carrying bits, just as you would in decimal arithmetic. You can see this by checking the binary addition at the bottom left, and converting that conversion of this result to digital form gives you what is shown on the right. There are similar rules, of course, for things like multiplication and other arithmetic operations. One can build on this to create signed integers, using one bit, typically the highest order bit, to represent the sign, positive or negative. And one can extend this to represent real or scientific numbers and to represent encodings for characters, using some high order bits to denote a character and then using some standard encoding to relate bit sequences to actual characters. The problem is that this is clearly too low level. Imagine trying to write a procedure to compute square roots, where all you can think about are operations on individual bits. This quickly gets bogged down in details and is generally mind-numbingly boring. So we need to incorporate a level of abstraction. We're going to assume that we are given a set of primitive objects and a set of basic operations, and we're going to build on top of that level of abstraction to deal with higher level languages for computation. So we will assume that our language provides a built-in set of data structures, numbers, characters, and Boolean values, things that are true or false. And we will assume that our language provides a built-in set of primitive operations for manipulating numbers, characters, and Booleans. Our goal is to build on top of this level of abstraction to capture the essence of a computational process. Thus, we are going to first describe our language for capturing computational processes, and then look at using it to solve problems. In this course, the language we are going to use is called Scheme, a variant of a language called Lisp, both of which were invented here at MIT some time ago. Everything we write in Scheme will be composed of a set of expressions, and there is a simple set of rules that tell us how to create legal expressions in this language. These rules are similar to the syntax of a natural language like English. They tell us the simplest legal expression and give us rules for constructing more complex legal expressions from simpler pieces. Similarly, almost every expression in Scheme has a meaning or value associated with it. The semantics of the language will tell us how to deduce the meaning associated with each expression, or if you like, how to determine the value associated with a particular computation. In Scheme, with only a few exceptions, we will see that evaluating every expression results in a value being returned as the associated meaning. Now, as we build up our vocabulary in Scheme, we're going to find rules for syntax and semantics associated with each new type of expression. Finally, we will also see that every value in Scheme has a type associated with it. Some of these types are simple, others more complex. Types basically define a taxonomy of expressions and relate legal ways in which those expressions can be combined and manipulated. We'll see that reasoning about types of expressions will be very valuable when we reason about capturing common patterns of computation inside of procedures. As we build up our language, looking at the syntax and semantics of expressions in that language, we will also see that these expressions very nicely break up into three different components. We have primitives, our most basic atomic units on top of which everything else is constructed. We have ways of gluing things together, our means of combination, which tells us how to combine smaller pieces to get bigger constructs. And finally, we have means of abstraction, our way of taking bigger pieces, then treating them as primitives so that they can be combined into bigger constructs, while burying or suppressing the internal details of the pieces. Let's start with the primitives, the basic elements. These are the simplest elements on top of which we will build all our other computational constructs. The simplest of these are the self-evaluating expressions, that is, things whose values are the objects themselves. These include numbers, strings, and Booleans. Numbers are obvious and include things like integers, real numbers, scientific notation. Strings are sequences of characters, including numbers and special characters, all delimited by double quotes. These represent symbolic as opposed to numeric data. Booleans represent the logical values of true and false. These represent logical as opposed to symbolic or numeric data. Of course, we want more than just primitive objects. We need ways of manipulating those objects. For example, for numbers, we have a set of built-in or predefined procedures. Thus, the symbol plus is a name for the primitive procedure or operation of addition, and similarly for other arithmetic operations, including comparison operations. Strings have an associated set of operations for comparing strings or extracting parts of strings, and Booleans have an associated set of logical operations. Think of these as abstractions. They're machinery that perform the operations described by a set of known rules. Before we actually show the use of these primitive or built-in procedures, we pause to stress that these names are themselves expressions. By our earlier discussion, this suggests that the expression plus should have a value. This sounds like a strange thing for many computer languages, but in Scheme we can ask for the value associated with a symbol or name. In this case, the meaning or value associated with this built-in symbol plus is the actual procedure, the internal mechanism, if you like, for performing addition. In fact, our rule for evaluating the expression plus is to treat it as a symbol and look up the value associated with it in a big table somewhere,
Shortly, we'll see how that table is actually created. Given numbers and simple procedures, we want to use them together. Ideally, we should be able to apply operations like times or plus to numbers to get new values. This leads to means of combination, our way of constructing large expressions out of simpler ones. In Scheme, our standard means of combination consists of an expression that will apply a procedure to a set of arguments in order to create a new value. And it has a very particular form, consisting of an open parenthesis, followed by an expression whose value, using the rules we are describing, turns out to be a procedure, followed by some number of other expressions whose values are obtained using these same rules, followed by a matching close parenthesis. This form always holds for a combination. So there's the syntax for a combination. An open paren, an expression whose value is a procedure, some other set of values, and a close paren. What about the semantics of a combination? To evaluate a combination, we evaluate all the sub-expressions in any order using the rules we're developing. We then apply the value of the first expression to the values of the other expressions. Now, what does apply mean? For simple built-in procedures, it just means take the underlying hardware implementation and do the appropriate thing to the values. For example, add them, multiply them, and so on. This idea of combinations can be nested arbitrarily. We can use a combination whose parts are themselves combinations, so long as the resulting value can legally be used in that spot. To evaluate combinations of arbitrary depth, we just recursively apply these rules, first getting the values of the sub-expressions, then applying the procedure to the arguments, and further reducing the expression. So, for example, to get the value of the first expression here, we get the values of plus, by lookup, and 4, because it's self-evaluating. Because the middle sub-expression is itself a combination, we apply the same rules to this, to get the value of 6 before completing the computation. So far, we have basic primitives, numbers and simple built-in procedures, and we have means of combination, ways of combining all those pieces together to get more complicated expressions. But at this stage, all we can do is write out long, complicated arithmetic expressions. We have no way of abstracting expressions. We would like to be able to give some expression a name, so that we could just refer to that name as an abstraction and not have to write out the complete expression each time we want to use it. In Scheme, our standard way for doing that is to use a particular expression called a define. It has a specific form, an open parenthesis, as before, followed by the keyword define, followed by an expression that will serve as a name, typically some sequence of letters and other characters, followed by an expression whose value will be associated with that name, followed by a close parenthesis. We say that this expression is a special form. This means it does not follow the normal rules of evaluation for a combination. We can see why we want that here. If we applied the normal rules for a combination, we would get the value of the expression score and the value of 23, and then apply the define procedure. But the whole point of this expression is to associate a value with score, so we can't possibly use the normal rules to evaluate score. Instead, we will use a different rule to evaluate this special form. In particular, we just evaluate the last sub-expression, then take the name without evaluating it, score in this case, and pair that name together with the deduced value in a special structure we call an environment. For now, think of this as a big table into which pairings of names and values can be made, using this special define expression. Because our goal is to associate a name with a value, we don't actually care what value is returned by the define expression, and in most Scheme implementations we leave that as unspecified. Thus, our means of abstraction gives us a way of associating a name with an expression, allowing us to use that name in place of the actual expression. Once we have the ability to create names and give names to values, we also need the ability to get the value back out. And that's easy. To get the value of a name in Scheme, we simply look up the pairing of the name in that table that we created. Thus, if we evaluate the expression score, we simply look up the association we made when we defined score in that table, in this case 23, and return that value. Note that this is exactly what we did when we dealt with built-in primitives. If we give the name plus to Scheme, it looks up the association of that symbol, which in this case is the built-in addition primitive, and that procedure is then returned as the value. And thus we can now use names in any place we would have used its associated expression. In the example shown here, we can define total to have the value of the sub-expression shown, and by our previous rules, we know that this reduces to 25. If we evaluate the last expression, our rules say that we first evaluate the sub-expressions. The symbol star is easy, as is the number 100. To get the value of the last sub-expression, we recursively apply our rules. In this case, looking up the value of score and the value of total, then applying the value of slash to the result, and finally applying the multiplication operator to the whole thing. Notice that this creates a very nice loop in our system. We can now create complex expressions, give them a name, and then by using that name, treat the whole expression as if it were a primitive. We can refer to that expression by name, and thus can write new complex expressions involving those names, giving the resulting expression another name and treating it as a new primitive, and so on. In this way, we can bury complexity behind the names and create new primitive elements in our language. So here's a summary of the rules of evaluation we've seen so far. For self-evaluating expressions, return the value. For names, return the value associated with the name in the environment. For special forms, do particularly different things. And for combinations, evaluate all the sub-expressions in any order, and then apply the operator, or first sub-expression's value, to the values of the operands. Because these ideas of evaluation are important, let's take another look at what happens when an expression is evaluated. Remember that our goal is to capture computation in expressions, and then use those expressions to compute values. We have been describing both the forms of the expressions and how one deduces values of expressions. When we consider the second stage, we can actually separate out two different worlds, or two different ways of looking at what happens during evaluation. One world is the visible world. This is what we see when we type an expression at the computer and ask it to perform an evaluation, leading to some printed result. Below that world is the execution world. This is what happens within the computer. We'll see a lot more details about this later in the term, but this includes both how objects are represented and how the actual mechanism of evaluation takes place. We want to see how these two worlds interact to incorporate the rules of semantics for determining values of expressions. When an expression is entered into the computer from our visible world, it is first processed by a mechanism called a reader, which converts this expression into an internal form appropriate for the computer. That form is then passed to a process called an evaluator. This evaluator encapsulates our rules for evaluation and reduces the expression to its value, using exactly the rules we've been talking about. Note that this may involve a recursive application of the evaluation rules, if the expression is a compound one, as we saw with our earlier nested arithmetic expressions. And the result is then passed to a print process, which converts it into a human-readable form and outputs it onto the screen. Suppose, for example, we type the expression 23 into the computer and ask for its value. The computer basically recognizes what type of expression this is, self-evaluating in this case, and therefore applies the rule for self-evaluating expressions. This causes the expression to be converted into an internal representation of itself, in this case some binary representation of the same number. For self-evaluating expressions, the value is just the expression itself, so the computer simply returns that value to the print procedure, which prints the result on the screen for us to see. A second kind of primitive object is a name for something, typically created by evaluating a define expression. Remember that a define created a pairing of a name and a value in a structure we call an environment. When we ask the computer to evaluate an expression such as pi, it recognizes the type of expression, a name, and applies the name rule. This causes the computer internally to find the pairing or association of that name in the environment and to return the value that is part of that pairing as the value of the expression. This gets handed to the print procedure, which prints the result on the screen. Note that the internal representation of the value may be very different from what is printed out for us to see. What about special forms? Well, the first one we saw was a define. Here the rules are different. We first apply our evaluation rules to the second sub-expression of the define. Once we've determined that value, we then take the first sub-expression without evaluation and create a pairing of that name and the computed value in a structure called an environment. Since the goal of the define expression is to create this pairing, we don't really care about the value of the define expression itself. It's just used for the side effect of creating this pairing, and thus typically we leave the value returned by a define expression as unspecified. So let's see what happens in our two worlds view. Suppose we type in a define expression and evaluate it. What happens? Here's an example. The evaluator first identifies the type of expression, in this case by recognizing the keyword define at the beginning of the compound expression. Thus it applies the rule we just described. As we saw, the evaluator now takes the second sub-expression and evaluates it, using the same rules. In this case we have a number, so the self-evaluation rule is applied. That value is then paired with the name, or first sub-expression, gluing these two things together in a table somewhere. We don't worry about the details of the table or environment for now. We'll discuss it in detail later in the term. As noted, the actual value of the defined expression is not specified, and in many scheme implementations we use a particular undefined value. As a consequence, the value that gets returned back up to the visible world may vary in different implementations of scheme. Most versions of scheme will show us some information about what binding was just created, but in general we will not rely on this, since it does vary with implementations. These rules hold for any expression. If we just have a simple computation or combination involving a built-in arithmetic procedure, we know that we get the values of the other sub-expressions using the self-evaluation rule, then apply the value associated with the symbol plus to those values, thus executing an addition operation. But suppose we do something strange like this. Our rule for defines says that we get the value associated with plus and bind it together with the name Fred in our environment. Remember that plus is just a name, so we use our name rule to find its value, which in this case is actually the internal procedure for addition. Now, let's apply Fred to some arguments. Notice that this just appears to be doing addition. Is that really right? Yes, it is, and let's think about why. Well, our rules really do explain this. The define expression says to pair the name Fred with the value of plus. Note that plus is just a name. It happens to be the one that was created when scheme was started. Its value, we saw, is a procedure, the internal procedure for addition. Hence, the define expression creates a binding for Fred to addition. Thus, when we evaluate the combination, our rule says to get the values of the sub-expressions, and hence the name Fred is evaluated using the name rule to get the addition procedure. This is then applied to the values of the numbers to generate the displayed result. As an example, if I ask for the value associated with one of these built-in names, my rules explain what happens. Since this is a name, its value is looked up in the environment. In this case, that value is some internal representation of the procedure for multiplication. For example, a pointer to the part of the internal arithmetic unit that does multiplication. That value is returned as the value of this expression, and the print procedure then displays the result, showing some representation of where the procedure lies within the machine. The main issue is to see that this symbol has a value associated with it, in this case, a primitive procedure. Thus, what we have seen so far is ways to utilize primitive data and procedures, ways to create combinations, and ways to give names to things. In the next section, we'll turn to the idea of capturing common patterns in procedures.